Hello, everybody. So we are still talking about the correlations of mass transfer coefficient for different geometries, and in this video we are going to discuss the case of mass transfer coefficient outside a solid cylinder. So in this case you have a solid cylinder where a gas is flowing outside. This is for gas phase only. This is what we are gonna or the equation that we are discussing now is for gas phase only. So we have a gas that is flowing outside the cylinder. There is a mass transfer process taking place between the outer surface of the cylinder and the air, either from or to. And we want to calculate the mass transfer coefficient in this case, and the correlation that we can use is this correlation that we see here. It doesn't look like the shape that we are used to, but you can see here that there is constant multiplied by Reynolds power another constant, and there is Schmidt here. So if you take Schmidt to the other side, it's going to be very close. And still, this K over V or KGP over GM is not exactly Sherwood number, but it's very close. Maybe this constant contains something that will make the shape a little bit different. But again, all these shapes are produced, or the equations are produced by or from experimental results or from experimental data. That's why the shape might be a little different. Anyway, so we have two alternatives, one for calculating the mass transfer coefficient Kg, and one for calculating the mass transfer coefficient Kc. This Kc and Kg are for the same phase, depending on the difference is what is the driving force. Is it the difference in concentration or the difference in partial pressure? But anyways, the shape here contains Kg multiplied by P, which is total pressure, Schmidt number power 0.56 divided by Gm. This is Kc multiplied by Schmidt number power 0.56 divided by V infinity, which is the gas phase velocity or the fluid velocity, normal to the cylinder, of course. This Gm is called the superficial molar velocity of the gas, normal to the cylinder. This is another way of representing the velocity, but it takes into account it's in the terms of the molar velocity, which is how many moles per second per unit area. This is how we define it. There is a relation between Gm and V infinity. These two are kind of alternatives depending on the equation that you use. They both represent the velocity of the gas, either clearly as a velocity or as molar velocity per unit area. And we will see how to calculate this Gm later, but this is just to keep this in mind. Reynolds is Reynolds number. It's rho VL over mu. This V infinity is the gas phase velocity, and the D is the characteristic length. Here is the diameter of the cylinder. It's not the length. It's not the length. It's the diameter. And this, of course, this mu, rho are all for the gas phase stream, because or depends if I have, but we said this is gas phase, so this is going to be a gas phase properties. The density, the viscosity are gas phase properties, and of course for Schmidt number, the diffusion coefficient here would be the gas phase diffusion coefficient as well. This equation is valid for Reynolds number from 400 to 25,000, and for Schmidt number from 0.6 to 2.6. So these are the information that we need to know about this equation. We don't need to know anything else. And again, just to repeat the same point that we or that was raised before, that in this chapter we just see the equations. We don't care how these equations came from, what kind of experiments that were done. This is another story, and this is out of the scope of this course. We just want to see how to to get an idea about the equations and see how to use these equations in case we need to use them in the future. So let's take an example here for a cylinder that's used in a humidification process. And humidification is simply increasing the humidity of air. So this takes place by evaporating water. So you increase the mole fraction or the partial pressure of water vapor in airstream. So this is simply the humidification process. So in this process, we have liquid water flows in a thin film down the outer or outside of a vertical circular cylinder. So this is what you see here. This is a cylinder a vertical cylinder, you have water that is flowing from the top of this cylinder and it flows on the outer sides of the cylinder. We know that the airstream outside is flowing perpendicular to the cylinder, or normal to the cylinder. We know the diameter of the cylinder, we know the length, we know the pressure, the temperature of the air, and the velocity of air, which is 4.6 meters per second. The liquid film temperature is 290 degrees Kelvin. This is the water temperature. This is the liquid phase temperature, which is 290. The gas phase is 310. And we said before that we do the calculations for the film, not the liquid film, but the film, which we said about the film theory, which we will get the temperature from the average of the two temperatures. And we discussed this in details before. So what we need to know is how much water should I supply from the top of the cylinder, so that this water will totally evaporate by reaching the end of the cylinder, and we will not have water dripping from the cylinder. So simply this means that I want to make sure that what I supply equals the water that will evaporate from the cylinder. This is simply what the problem is about. So I have here all the information on the left hand side of this screen here. So we have the temperature of water, the temperature of air, the pressure, the gas velocity, the diameter, the length of the pipe. It's dry air, so the partial pressure of air outside the cylinder is 0. The partial pressure of air at the surface is the saturation pressure, which you can get from any textbook or from any physical properties data book, or from Antoine's equation, whatever the source. You can get this value. You have the film temperature is going to be the average of the liquid and the vapor phase, or the gas phase, the air and water, which is 300. And at this temperature we can go and check the physical properties of water. And again, this is water, it's not of air, not water. We have here at the 300 degrees Kelvin, we have already the value, so I don't need to do any interpolation. This is the density, this is the viscosity, this is the kinematic viscosity, or the momentum diffusivity. So we have all the values here. So what we need to do is to write the balance equation. The balance equation states that the water supplied to the cylinder equal the water evaporating from the cylinder. This is what the problem is all about. The supply of water to the evaporation of water is the flux multiplied by the area. The flux is the mass transfer coefficient multiplied by the driving force, and this is the area. Looking at this equation and all the information that we have everything except for kg. So this is the only missing parameter here. So to get the kg, we will use the correlation, and this correlation contains some parameters. We need to make sure that we have everything. We have P, we have Schmidt number, only is missing the diffusion coefficient. Reynolds number, I think we have everything for Reynolds number, so we will see. So first let's get GM, and GM, as we said before, it has units of mole per meter square second. This is the units of GM, and we said this is another representation of the velocity. So of course this GM will be calculated using an equation that contains the velocity as one of the parameters here. So what you will need to do is just to see the parameter, or multiply or divide by other parameters that will make the units match what we are looking for. So the velocity has units of meter per second. You want to convert this into moles per area per time. So what will convert the velocity into mass is the density. This is what you will think of. There is no other option for you. So the mass, if you multiply the density by the velocity, it's going to be mass per unit area per unit time. I'm getting very close, but I need it to be in terms of moles. So to convert the mass into moles, I divide by the molecular weight. So this will be moles per meter cube. If you multiply mole per meter cube by meter per second, it's going to be moles per meter square second. So this is GM. So GM is the density of air multiplied by the velocity divided by the molecular weight of air. And of course the molecular weight of air is known to be almost 29. So I have GM. Now I need to calculate the diffusion coefficient. I know the diffusion coefficient, if you check the appendix in the end of the textbook, you would see that there is or there are already values for the diffusion coefficient of water vapor in air. But this is at 298 Kelvin, so you need to multiply it by T over T power 1.5, as we discussed this in chapter 22 in the very beginning of the course when we were discussing the liquid phase or the gas phase diffusion coefficient. And we said that the diffusion coefficient is directly proportional to T power 1.5, and that's why we use this relation. Of course, omega d will not be of a big difference because of this small difference in temperature, so you don't need to do it. So this is the value of the diffusion coefficient. I have almost everything now, so I can calculate Schmidt number, which is the momentum diffusivity divided by mass diffusivity, is 0.6, and Reynolds number is going to be V infinity multiplied by D divided by nu, and this is 22,283. So these two values are within the range that this equation is valid at. So this equation is valid within this range, so this makes the equation okay. So what we'll do now is direct substitution in the equation. We have all the parameters. By direct substitution you can simply calculate the value of kg, and from kg you can substitute in the equation. We have everything now, and now you can calculate the amount of water you need to supply in kilogram moles per second, or you can divide by the molecular weight to get it in terms of kilograms per second. And this is all what we need to do to calculate the amount of water that we need to supply in order to get all the water evaporate by the end of this tube. Next time we will move to another point where we will, or another case where we will do the calculations of the mass transfer coefficient through pipes in a flow inside the pipe, for a flow inside the pipe. Just to be moving with the or following what we have with what we covered in the slides with the file for the correlations, we are done with this part here. So this is the mass transfer coefficient for flow normal to a closed cylinder. This is for gas phase, and this is the equation. This is the conditions. And next time we will go inside the cylinder. So this is outside the cylinder. Next time it's going to be inside the cylinder, and we will see the different cases of the equation that we can use. So this is going to be the topic of next time, inshallah. So I'll see you then.